So this next xaq-ai diary entry is my first attempt to try to close that loop and use the EPM and lateral voting and an action controller to play the game of Pong. It was way too early, but I had to just jump in and try it. It's frustrating. You'll see how things worked and how they didn't work. I think I do a pretty good job of explaining it. Let's check it out.
All right, so this is a quick and dirty update of Amy Agma version 2. Everything I've built so far because I'm getting ready to refactor for version 3. So just a diary entry for where we're at right now. So in our main EPM tuning application here, we've added a whole bunch of very interesting things. Obviously, we can have video input now. That could be your webcam or something like that. And we have a whole bunch of new encoders for video and for audio. And one of the main things I was really trying to get working is the true active inference loop by learning how to play Pong. So if I launch the breakout Pong game here, we get to hear the sound that I've been listening to over and over and over again, which is the sound of Pong doing its thing. Now, what I would do, which I understand now is really not the right approach, but it was good for experimentation, is to actually train on the sounds and the video of this breakout game. So if I want to do that with the video, I could just refresh the devices. I can launch into the Break Pong. Now I've got that as video input, and I can train or at least just observe the behavior of what each of these encoders do inside of the context of this game. So one of the encoders I've been working on the most are the dorsal and ventral, in order to get some information into the system about where is the ball on the screen, what is it doing, and try to predict its motion. So if we look at the dorsal encoder here, yeah, I'm just going to hit play, and it's going to do its bootstrapping thing, even though I know now that's probably not going to be necessary, but we're running through bootstrapping, and it's creating its embeddings and it's creating its knowledge graph. Now, one of the issues I know is happening now is, well, this knowledge graph isn't looking too bad. It does cycle through the knowledge graph as far as moving from point to point rather than just making a cloud of randomness. But not super happy with this because you can see how these nodes are very close together. They should be wider apart. But we're actually building a knowledge graph of this dorsal optical flow encoder, and you can see the things that are moving are what's showing up here. So at least the Python version, is working correctly. Now, when we're done with this, I can just hit stop. Say we want to export it. Obviously, we could save the brain state like before, but we also have now exporting to C++. And we have a fairly robust way of exporting this entire configuration into the C++ version and actually doing some parity checking against the... actually, I'm going to turn this thing off for now because it's so annoying. Doing some parity checking between the Python version and the C++ version. So that's all well and good. We can take a look at the ventral one as well. Actually, I'm going to reset the graph because we definitely want to do that. Reset the brain. And what we'll do is I'm pretty sure this thing doesn't need training. It looks a little dark here. Let's see. Yeah, but it still should be working. So ventral should be working better than this, but look at this. We've got these weird oscillations here. This as a detector needs to be fixed up. However, when it is working, we've got these nice chains that are made, right? So, but then it stops. it's got sort of like a general idea of what's happening on the screen. Is it identifying the ball? I'm not really sure, but we're going to dial in these encoders to be a lot more robust and also not require Onyx anymore. That's going to be one of the big changes that we make, because this is holding no information. It's just oscillating between these two nodes as this thing goes up and down. If I turn up the sensitivity, right, the detail amount of each node, it's still not really breaking out of it. Not ideal. It's not how we want that encoder to work. So that's obviously kind of collapsing our workspace here. The other encoders, saliency was also one that should be a little bit better. So this one's bootstrapping now. We'll see how it behaves. So this one's kind of similar. It's like a whole bunch of interesting changes that happen. Looks like a dead spider. Everything's coming off of the middle there. So I don't know. Maybe this one's encoding fairly well. But we're going to be moving away from these neural network type encoders and going towards geometric ones. So hopefully we'll get the same thing. They'll be a little bit more lightweight. They can run even faster on embedded devices. So this is building a knowledge graph that isn't terrible. But the problem is it doesn't work as, we have to export the encoders as Onyx, and when they run in C++, they just don't behave the same way that they do here in Python. Not entirely sure why. I mean, just the general, it's ported, but there's just like not exactly the same kind of behaviors, especially when they're running autonomously. So, but let me demonstrate that because I think it's important. So I'll save this one to C++. Great. All right, so now let's do the end-to-end testing. I think this actually was really interesting. We learned a lot doing real end-to-end testing. I'll show you how it works, and there's some obvious pitfalls, but let's check it out. So let's go kill our game here. So what we're going to do is we're going to run our setup for the end-to-end breakout. So what we were able to do to create this end-to-end, so what's going to be happening is you can decide what EPMs are actually running. I'm going to say all for now. I'm going to turn on my sound. Now, how many minutes of passive observation? We're going to use 2 minutes. And do we want to run with fresh graphs? I'm going to say yes, because that actually is the right approach for what we're trying to do. That tabula rasa, starting off with absolutely nothing and hopefully learning how to play a game, right? So I'm going to talk through some of the problems that I see, but we're just going to get this thing started off. So it's going to launch our brain server. This is the brain server. And it's going to connect up our EPMs here. Okay, I'm talking into the cochlear node, which is going to cause it to make some weird stuff, but I'm going to go over to voting controls. And what we're seeing happening here is the reality tokens that are emitted from each from each of the EPMs. We also have a proprioceptive node, which is right now just a test one. It's emitting real reality tokens, but it's actually getting the position of the paddle as a proprioceptive feedback from the game itself, right? So obviously that's going to be an EPM because we want this thing to be fully fractal and buildable. But what you can see happening is that we've got, real paddle positions, and then we actually, optical flow, cochlear, the retinal. Where is our? So saliency. Look, it's stuck. It's stuck between, just basically stuck on node 0. Optical flow seems to be the one that's working the best. And we've got good resonance. The whole thing does resonate. There's a lot of like correlations here. I'm going to turn the temporal horizon. Actually, 700 milliseconds isn't bad. Hebbian threshold can be a little higher. Get it there right at the resonant point. I'm going to reset the consensus history. Now that everything's up and running. Okay, we can see our consensus tokens. The full dimension, the full 768 vector as they're being generated here. You can see the learning rate's actually pretty low. And we also have this retroactive look back. This is sort of an attempt at some RL. I'm going to turn that down to 10. Okay, so in its current state, this paddle is pretty stuck. So right now it's in active inference mode. You can see it actually switched over to single player mode. And at this particular version, it's basically in this kind of just oscillatory state. And that's because we really don't have this thing responding to TLE properly. There's a lot of problems with it, right? We've got good resonances here. But what it's not doing is translating into real body motion that isn't finding a local minimum, right? Basically, we've got lazy robot syndrome, and it's stuck. So we can go to active inference, at least look at what's trying to happen here. Let's see here. Yeah, it's trying to localize onto this, but it's actually not translating into motion. I did have it moving more, but it was never anything other than random or stuck, right? So I can make this thing move even more, but you can see we're very much in this sort of like stuck state. I can try to get it to move a bunch, but it's really this is not moving because of the ball. Let's just put it that way, right? So when it does hit when it does get a foul, or when the ball does go past, we can see that it does spike the learning rate. We've tried me and Gemini have tried a couple different things as far as like changing the learning rate to make it babble more when it misses. So you see we've got a spike here, but it hasn't really translated into better babbling. This particular version is really just kind of stuck. So that's where we're at now. And really what this thing needs to be is I'm going to rebuild it with the true intent of, I'm turning this annoying sound off. So annoying. We're going to rebuild this with the true intent of the final system, right? So I'm going to modularize all of the true components that we're looking at here, right? So we have the lateral voter. So all the EPMs come into the lateral voter. That's going to be its own module, right? So you can actually build this Hebbian network here. Now, one of the phenomenons that basically ended up happening is we have this cycle of it builds up the graph, because randomly it hits the paddle, right? Oh, we're at 21%. So it's building all these Hebbian associations here in the graph. However, as soon as it starts missing again, because we have our attempt at RL here, this retroactive look back, it degrades them. And then it builds them up because it's random, and then it builds and they go down. It just does that over and over and over again. Kind of the most complicated random noise generator. You can see like, okay, it just got penalized. It decreased, but then it randomly hits it because it's just making noise. So this doesn't even have 22% accuracy. That's basically just noise. Until we get past 50%, this thing isn't doing anything other than just screwing around. So anyways, what we're going to do is we're going to modularize everything. Everything's going to be C++, super fast. I'm going to make unit tests for every single component. So, every EPM is going to have the mitosis gatekeeper, which is going to look at its complexity, right? It's going to look at the complexity versus the stability and actually prune nodes that way rather than just are they stale or have they not been activated, right? So that's going to be a nice stability improvement just inside the EPMs. Like I said, all of the encoders are going to become geometric rather than relying on neural networks and these pre-trained encoders. And yeah, that the good thing is that means that none of the encoders are going to require any kind of training, right? So they'll be able to just, the theory here is that it's going to be able to play any kind of video game. You just turn this thing on, it's going to learn it. You throw another video game at it. Oh, this is different, and it learns and play that, right? That's what we want. There's also going to be the consensus gatekeepers. So I tried to build all of these things that kind of merge the EPMs together into this one app. But really, they're supposed to be separate modules because there's a mitosis gatekeeper that actually spins up new EPMs when necessary to connect to the existing encoders and actually, continue to build the knowledge without any kind of intervention or tuning or anything, right? So, yeah, this is basically where version 2 is stuck now. I'm not even going to try to get it to work because, there's definitely things I could do to try to keep hacking at it, but really we just need to move on. We know the EPMs work. We know that the whole idea of having this fractal JEPA concept is working. We can get EPMs to resonate together. This timeline display is kind of like computationally intensive, but it's a nice way of looking at it. Looking at active inference this way is kind of cool. So we've got some interesting visuals that we can play around with. But really, I want to see this thing play games. I want it to be working properly. The end goal here being more and more complex games, really embodying a player character, and then finally robotics. So that's where we're at. I think that's really all of the things that matter. Oh, just a side note: everything in this version 2 is communicating over UDP, so it is chewing up the network. Because the idea was that I was going to run it on a Raspberry Pi, but if everything's in C++ and it can run locally, well, I don't even need UDP, right? Pretty sure everything that we're looking at right now can run on a Raspberry Pi. We don't even need to communicate with the brain or communicate with a PC, right? Everything just runs on it. Here, let's just take a look at BTOP here, see how much CPU we're using. So we got our EPMs here. These are all different processes. Yeah, they're just not using that much. Some of these are using a decent amount of memory, but that's because they're running Onyx models and stuff, right? This anti-gravity. We got this one here. So yeah, 63 megabytes. Yeah, I think we can do better than that. These things don't need to be this big. Not if they've got geometric encoders. All these things should just use a few megabytes, right? However, the knowledge graph does matter. So each of these have not created giant knowledge graphs. Only tens of nodes. Optical flow is the only one that gets higher than like 10 because like saliency is stuck. It's stuck at 0. Proprioceptive looks, it's stuck. Yeah. Anyways, this thing's not using a ton of, it's just, it is chewing up the CPU, but not in any kind of crazy way. So this will definitely run on the edge. No doubt about it. It's going to be good. Anyways, that's where we are now. Another refactor, but for good reason. So, all right, that's it for now.